Hello, my name is Simon Tong, and this is my lab report number 4 for Physics 2212. So this lab was all about circuits. The first part of this lab was to show the potential difference throughout a circuit along different aspects of a circuit, such as the battery, resistors, or even the wire. So we looked at how current changes in parallel versus series circuits as well as the round-trip electric potential. And the round-trip electric potential is always going to be 0 if you start and end at the same place. We then looked into RC circuits, first the charging of a capacitor and how a light bulb is affected, and then also the discharging of that capacitor and how a light bulb is also affected. And then finally we plotted potential difference versus time to show the constant RC, or time constant. So the setup. That first picture there is the initial setup measuring the current, and you can take note that the current is 0.02 amps read through the ammeter. We then switched the direction of the ammeter, and that did not affect the current whatsoever. We then brought out a voltmeter, and the voltmeter found or measured the potential difference between any two places in the circuit, and as you can see in the picture, it does not bridge the wires, but does show the potential difference between the two. We then moved on and had the RC circuit set up with the capacitor charging, and you can see the light bulb is dimming there. So a couple of physics principles we used. We used the energy conservation principle and the loop rule, which is that the sum of potential differences across the complete loop of the circuit should equal 0. Like I did mention in the overview. We also used the current conservation rule, which is the node rule, which is the sum of the current across multiple loops of the circuit should be 0. We also used Ohm's law, which says that the potential difference V is equal to the current times resistance. So the data collected from the series circuits. The first two circuits made were circuits in series. And the potential difference between each 2 points was graphed, as you can see on the bottom right graph. And the raw data from that is actually shown on the far right. The only thing changing potential difference was the batteries and the resistor. The wire and the ammeter did nothing to change the potential difference. We then found the resistance from Ohm's law. So resistance equals the change in potential difference divided by the current. We got for the resistance in the 47 ohms resistor to be negative 47.95 ohms, which is very close to 47. And then we got the resistance in the 100 ohms resistor to be negative 102.05 ohms, which again is very close. And the resistance in the wire and the resistance in the ammeter were both 0. We then set up the RC circuit and made a couple of notes about it charging and discharging. When the circuit is first connected and the capacitor starts charging, the light bulb starts out very bright and dims as the capacitor charges more and more. However, when it's fully charged to discharging, the light bulb again starts out very bright and dims as the capacitor loses more and more of the charge. We then measured the potential difference across the capacitor over a 20-second period of time and graphed the ln of the potential difference divided by the initial potential difference versus time. As you can see, that plot is on the right. The slope of this graph was negative 0.132, and that was equal to negative 1 over RC. We then solved for the time constant RC and got 7.58. On to our what-if questions. The first being, what if you were doing this lab in real life and used an actual ammeter instead of an ideal simulated ammeter? What's different about a real ammeter, and how would it have affected the circuits you hooked it up to? Well, a real ammeter would have had some actual resistance across it as compared to the ideal ammeter used in the simulation, which did not have any resistance. It would have increased the resistance across the circuit and made the current less. The second question was, what if you were doing this lab in real life and used a real battery to charge a real capacitor with no resistance in the circuit? How quickly would our ideal model predict the capacitor to reach full charge? Would this prediction happen in real life? The ideal model would say that this situation would happen instantly, but in real life there is resistance in the wire and the battery. This means that without a resistor present, it would take some finite amount of time for the capacitor to reach full capacity. So that's all. Thank you for listening.